Hello, again for Unit 1, Chapter 2. We're going to be talking about matter, some of the ways in which we find it and separate it, and ways in which we can differentiate between mixtures and substances. First off, how we view matter can change. It can be viewed in a number of different ways, but the more important thing we need to make sure that we understand is matter is anything that has mass and takes up space. That means most everything is matter. Even very, very small pieces of dust are matter. They might not have a lot of mass, they do take up space, and enough accumulates, such as enough underneath a bed. If you don't have enough stuff shoved up underneath there, you get those dust bunnies and they pile up. They don't take up a lot of space, they don't have a lot of mass, but they are still matter. You have how we view matter, or how we can see the matter, is three different methods. We have the macroscopic, and we can see that with our human eye, even if you have contact lenses, really bad vision, so you need glasses. It still talks about being seen with the eye. Contact lenses and glasses, as blind as you may or may not be, those are corrections. So we still use the can be seen with the human eye. We also have the microscopic, and that, just as it implies, it not too small to be seen with. It's too small to be seen with the naked eye, which meaning without any aid. And this can be done with just as small as a hand lens. It's not corrective; it's enhancing what we are seeing. And so you could have done this last year, or most likely in 10th grade biology, something through a microscope. You needed to see the cells, or parts of the cell, and that's done through the microscope. This can be as good as, say, with a scanning electron microscope, which we'll see down to smaller than a micrometer, which is a million times smaller than a meter, which is extremely difficult for us to wrap our hand around. But if you look at a millimeter, which would be about the size of a pencil lead, is usually about 0.5 to 0.7 millimeters. That's about a half of a millimeter, and you still have segments inside that. And you, with the scanning electron microscope, it can see all the imperfections on that piece of pencil lead that you would have. The particulates, and this is actually what I feel makes chemistry sometimes difficult, is the fact that we can't see it with an optical microscope. You need to envision, be able to view these things, imagine what these things are looking at through artist depictions and other methods. So they make up all of matter. Atoms, ions, protons, neutrons, electrons, they're all there. It's us trying to figure out how are they interacting without actually seeing them interact. And so it takes a very conceptual approach. And we'll need math, as we'll look at in the next unit, but you do need some math there because it's proven by math that these things do exist. They are be able to do some different kind of imaging to kind of show you some of the imperfections, that it shows that atoms are there. And we'll talk about in Unit 2 about the electrons and protons and the neutrons and how they actually were discovered. So we'll continue to talk about this, but this, I think, is be difficult for most students to understand, that the particulate matter, we can't. This is what chemistry is. We're talking about the particulate matter, and we can't see that. So in the lab, we work with macroscopic amounts of materials, but we have to still try to figure out what's going on at the particulate level. So we need some methods to help us figure this out. How do we get those mental images? What do we use? How do I look at that? What am I supposed to look at? We can all think of all these different things, but if we're not all thinking at least within the same idea or concept, we can have 30 different ways to view it in a class of 30 students. So scientists have come up with different ways to make sure that we're at least all thinking about the same thing. And that's what it is that we have models. Chemical formulas is one of the big ones. Do you see the chemical formula right here? The chemical formula, C is for carbon. The subscript 2 means that there's two of them there. The H is for hydrogen. The 6 tells us that there are 6 of them there. Now, how we know that, or how it's actually drawn out, is a number of different things called models. And so we have molecular models, and there's two types. The ball and stick model. We have ones that are very similar to this, and you can see the little hydrogens there, and you can see the carbon right there, the little black spheres right there, and so you see how they come together, and that's what we'll deal with in a later unit when we actually look at some of these structures and how they interact. The space filling model is a little bit different, where you have those blue right there, those are your hydrogens, and that green is your carbon. You can see that everything is still there. And this actually probably gives us a better depiction of what's actually happening than the ball and stick model. But we like the ball. I like the ball and stick model because we can see the bonds. There's still a lot of things that we can see within that I think they still hold a lot of value. Now, this is one of the first chem quandaries that we have, and copper, gold, and silver are far from being the most abundant metals on Earth. Aluminum, iron, and calcium are much more abundant. So we need to think, or in question, envision, and think about why this is. And you will actually have a question on your Schoology that will be asked of this. So if you could take time, fill out your 3 sentences as the why it is, why you think, and answer this question. Why are copper, gold, and silver among the first metallic ones to be discovered? So why are copper, gold, and silver discovered first as opposed to aluminum, iron, and calcium, which are much more abundant? Now we're going to look at some of the properties, and that kind of leads us into that. Those chem quandaries kind of usually will lead us into that, and some of them are reasons why that might be are actual, well, physical properties. You did a lot of physical properties or identifying of physical properties in usually in earth science, when you're 8th grade earth science, when you did your mineral identification or rock identification. Ones that we don't deal with a lot in there is the melting point and boiling point. We'll do more of that in this course. You dealt with hardness, such as Mohs hardness scale. Geologists have been known to smell their rocks. They're a little bit different. You did some specific densities. We'll discuss a density. Color, what did the rock look like, or what did the mineral look like? Same thing with the hardness. Did it scratch your fingernail? What color did it scratch the plate? Did it scratch glass? Did it refract light? Those are all physical properties. You not changing anything. You're just looking at it, such as holding it in your hand. Kind of physical properties are ways to identify the substance through your senses, but really just looking about eyes, because we know that we're not supposed to taste the chemicals. So the mass is a part of that, and that's kind of talking about the density is the amount of matter that is actually there. Volume is the amount of space that matter actually occupies. So those are parts of density that we'll talk about later, and some of these are extensive properties, meaning they depend upon how much you have there. How much a penny weighs? Well, it depends on how many pennies you have. If you have a roll of pennies, you could have 50 pennies, and therefore it's going to have a mass of blank. Whereas a single penny will have a different mass. And even pennies, even if you get into the different years of pennies, will have different compositions, different amounts of copper and zincs and things. So an extensive property depends on the amount of matter that is there. Extensive, how much is there. An intensive property is different. It depends on the type of matter. Hardness of a bowling ball is an intensive property. I like to use the example of the smell of banana bread. Most everybody enjoys the smell of banana bread. Now that is a intensive property. It's something that most, if not all, banana breads have. Now, how much that smell can travel will depend on how much banana bread you make. But the fact that you made banana bread, if you made just a small little sample muffin in your oven, it would still have a smell. Now it wouldn't be the largest smell. You wouldn't be smelling it down as you walk down the block, but it would still have a smell. And it's that fact that it has a smell. Density is an intensive property because it's based on a ratio of mass to volume. And these are little things that we'll continue to talk about, but we need to make sure that intensive properties depend on the type of matter, not how much is there. It's just the type. Here are some physical properties. It is not necessary to write down this whole table or chart, but it gives us an opportunity to look at some things, such as what does oxygen look like? Well, it's colorless. It's a colorless, odorless gas. It has a melting point of very small amount, meaning you can solidify oxygen. It's just going to melt at negative 218 Celsius. Now, you're right there, you are looking at probably 54, 55 degrees Celsius above what is known as absolute zero, 273. And so it is very, 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 very cold. And the boiling point of oxygen is, again, very, 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 very cold. None of you have experienced any of these temperatures that you would see here. We actually don't see realistic temperatures or realistic things until we get right around here. Times or things that we have actually seen. Most of us probably have never seen this solidifying of mercury, so that's probably not one that we'll ever see before. But there are some things that you will not fully get on that one. But we will see some parts of it, and so we do see it every now and then. But, bromine is a liquid. Water, that's the one that we see the most. Really saw those things. But then you get into sulfur where it doesn't melt until, where water's boiling. And so you kind of get in some of that. Look at how extreme those you get for melting of sodium chloride. I've seen this in a one. It's extremely hot. It really is. You have to actually grab the crucibles out with like a 3-foot crucible tongs. It is just crazy interesting. Which properties can be observed without changing the composition of a substance? Please answer. There are three main states. There are others. There's plasma, Bose-Einstein condensates, and all these other ones that you're dealing with extremes on that. And I feel those are great to understand and try to figure out. But I think if you don't understand what's going on at the particulate level with a solid, liquid, and a gas, those other ones become even more difficult to fully understand. So I think it's important for us as students to, as we progress through, to really have a good understanding of solids, liquids, and gases as they are just here. Solids are materials that are fixed shape, definite volume. The material not compressible. You can't crush it, and if you do, it actually just crushes. And we can see some quartz here, and we can see how all the little atoms are lined in nice little box cubic forms, and so some of those things we can see that, and so how those materials are. It has a nice shape, fixed volume, and so that non-compressible as well. Well, now that is different to say a liquid, where they have a definite volume but not a fixed shape, meaning if I poured this liquid into a different shaped vial, it would take the shape of that vial. The volume that I pour in will actually be the same. One thing that liquids, you have a solid and you have liquids, they are alike in that they have in their volumes, a definite volume. They both have a definite volume. That is how solids and liquids are the same, and they're also moving. And notice how these little spheres, you can see kind of they're just kind of moving around, squiggling around, just a little bit more often than the ones on the solid. Now a gas, they are even crazier. Look how an artist depicts just like drawing around, just flying around, zoom, 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 not paying attention to anything. And we see in here they don't have a shape and they don't have a volume, because if you take this rubber stopper out, all of a sudden that gas is going to, well, take and spread out into the classroom, wherever it is. The only way to actually get it to be right in there is to seal it in there. And so you now have a similarity between liquids and gases, and that is their no shape. They have no shape that is just theirs, whereas solids had a shape. So you have to be mindful. And so as we can see, when you went from a solid to a liquid to a gas, the shape went away, the energy increased as well. And that's a real big one, is that the energy was increasing as we went through. Now these phase transitions, some of you probably know them. A few of them are very noticeable, understanding, and that is solid to a liquid. Well, that's melting. Yes. Liquid to a gas, vaporization, sometimes called evaporation. I accept both. Technically, term vaporization, evaporation. We're speaking the same language. Gas to a liquid, condensation, condensing. Solid, liquid to a solid is freezing. Those are the very common ones that we see all the time. Going from a gas to a solid, deposition, kind of tough. That's one that requires a little bit more thinking, and so that's where we go with that. Solid to a gas. Sublimation. Usually you see this with solid carbon dioxide, also known as dry ice. So what's going on here? Well, it's a changing of the energies. So when we look at this, it's all about changing of energies. Are the particles going faster, or are the particles going slower? And you have to look at that and what is going on with that. Match the states of matter with the following descriptions. takes on the volume and shape of its container. 2. Has a definite shape and volume. Has a definite volume, but not an, but an indefinite shape, meaning no definite shape. Please answer. Now we can change some of these physical things, how they look. And it's a physical change, and it's a change in substance that does not change the composition. If you melt ice, well, someone will be like, well, it's not ice anymore. You're right, it's not ice anymore. But ice is actually just another term that we use for water. Water is the proper term, but we always think of water as something liquid that we can drink. And so water. No, that was liquid water. We have gas water, water vapor, steam. So we have this, that's why water is so confusing sometimes for students, in that there's so many different ways in which we say, oh, that's just solid water. Well, if you call it solid water, people are going to look at you weird. If you call it ice, people know what you're talking about. And so we have to be very careful that it doesn't matter what it is. In all cases, it is still H2O, dihydrogen monoxide, if you will. And so we have to be very careful. So if you take an ice cube and set it out on the counter, it's going to melt. That's gone through a physical change. It's not the same anymore in its physical state. It has melted. It's gone through a state change. And so a lot of times, physical changes are also state of matter changes. So those are important things to do, because I can also take a piece of paper, though, and rip it in half. It's been changed. I can color on a piece of paper. It's still the piece of paper. I've just colored on it. And so we have to, a lot of times it's easier for us to say, is it a state of matter change? Has that changed for us? Now, sometimes we have to identify the type of matter that we're dealing with, such as a mixture. Now, there are two types of mixtures that we deal with, but first off, we need to understand what a mixture is, and that's two or more pure substances that are combined. It is a physical blend. You take orange juice, for example. I love drinking orange juice. It's one of my favorite things to start off my day, is a glass of orange juice. That is a mixture. There's a lot of stuff inside there. And if you let some orange juice set long enough, you can physically see there's stuff inside there, the pulp and all that other good stuff with all those great vitamins for us. And so I have to mix it. And through mixing it, I am physically blending those components so that when I pour my glass of orange juice, I get a blend of everything, and so that everything is mixed in there, so that I'm not just drinking like a watered down stuff at the top, and then when I get to the bottom, I'm almost chewing my orange juice, which nobody really enjoys. So we're going to go over those parts, and so how they're the parts that break down a mixture are the components or phases or substances inside a mixture. And we'll look at each one of these types of mixtures individually as we go through. A homogeneous mixture is a mixture that it's the same throughout. Solutions are great examples of homogeneous mixture. Sometimes, though, we have to be careful about that, and that is if you take your Kool-Aid, as we can see in this picture here, and mix it, if you don't do a good job of mixing it, of blending it, it's not going to be a good homogeneous mixture. But if you do a good job of stirring it very well, blending it, it will become more of a solution. And if you let it sit long enough, especially for some people on how they make their Kool-Aid, they might put in a large amount of sugar. All that sits at the bottom. And nobody wants to drink the stuff at the top. You want to mix it up so that you can't tell the difference. Same composition throughout. You want to buy paint and have it shaken or stir it really good from the hardware store so that when you go to paint, it's the same composition throughout. Now, a heterogeneous mixture has different compositions at different points, and I use a bang trail mix here, and you have your dehydrated apricots, and you have some dates, and you have some pecans and walnuts, and ooh, a little cashew there, everybody's usual favorite. So we can easily pick out the little different parts of that, and so another good example of that would be if I say had a beaker of water. I got some water in here, and if I take and put in some red, you can see there's different parts in there. You can see and look at there's blue and there's red, and say maybe that's like a sand mixture, sand water mixture. You can see the differences between that. So you can see the things. There's different composition, different points, easily seeable, and you can open up a paint can. From the example from the previous one slide, is that we have different compositions as well inside there. So you need to homogenize sometimes those heterogeneous mixtures. You need to homogenize, blend them so that there is a same composition throughout. Now, you're not going to blend a trail mix. You're not going to do that so that it's all the same. That happens in your belly when you're eating it. So when we look at these mixtures, in that we have olive oil as a homogeneous mixture. Vinegar is, believe it or not, a homogeneous mixture of acetic acid and water, and we see there's two different things. But when we mix them together, they make a heterogeneous mixture. You can see the different phases, and you can see this little line right here that we have the oil on top and the vinegar on the bottom. And then you do that, and you can mix that up. You can shake it up really, 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 really hard. And it might look good, and that's the only way to really eat a good Italian dressing or oil vinaigrette dressing is shaking it up really good. But eventually they're going to set. And you have to shake it up again to get it to homogenize so that you can put it on your salad. And then you can go from there. But you have to, you still have, there you have this, looks like a homogeneous mixture, and then it comes and makes this heterogeneous mixture. Although you can try to homogenize it, it will eventually set out, just like, paint will do. Which of the following phrases describes a mixture? Composite varies. Composition may vary. Components cannot be separated. Which of the following is a homogeneous mixture? Vinegar, iron filings in sand, chicken noodle soup, muddy water. Now somehow we are going to make some of these mixtures, homogeneous mixtures and heterogeneous mixtures, and we need ways to separate them. And there are two different methods in which we can do this. There are a couple different ways in which we can use filtration. The most common way, where we're going to take and make this mixture here, and we're going to take that and we're going to pour it into a filter paper in a long stem funnel. here, and we have the funnel. You have the residue, the junk that we, in some cases, we want. In some cases, we don't want that. And so you have to be careful on what part of this do I want? Do I want the residue, or do I want the filtrate? The stuff at the bottom here in the test tube. And we'll go through, and this is labs, and through the labs, what we'll do is we'll set this up, and we'll see, and we'll do this one's more of what's known as a gravity filtration, where you have your filter paper, and you're using gravity to pull the filtrate out, and to separate that from the residue. Then you have a distillation. Now, this has to be done. You use a distillation to separate things based on their physical property, such as a salt water. It has two components to it. It has salt and water. It's homogenized. If it's a good saltwater solution, you can't tell the particles of salt that are in there. So the only way to separate them would be to evaporate that, or vaporize the water. And you're not going to have a vaporizing gun, pew, pew, but you can heat the water and heat it and heat it and heat it, and then you'll get that white crusty on the bottom of the pan that you probably have. Maybe if you set, we're boiling water for maybe some noodles or something like that, and you let it boil too long and you evaporate it out, and you get this white ring of salt that's in your water on the pan. And you're like, what happened here? Well, that's it. It's that separation of a homogeneous mixture. And so distillations work great for separating out homogeneous mixtures where we can't tell the difference between them. You can actually separate out, say, a ethanol and water mixture. It's very fine tuning, but they can be based on their boiling points. I think ethanol is about a 70 degrees centigrade boiling point, and water is about 100. And you can play around with that and slowly heat that solution up, and then eventually you'll get it at 70, and it'll actually kind of stabilize somewhere around 70 if you're doing it right, and then you will be able to extract the ethanol out of that solution. Now, some water will come over, and for analytical chemists, they have ways to change and figure out how all that works, but we're not going to worry about that. Which technique is used to separate homogeneous mixtures? Now, pure substances are not mixtures. They have a definite composition, uniform and definite composition. They might look like a homogeneous mixture, might look like a pure substance, but it's not. I prefer the term pure substance as opposed to just a substance, because there's some ways in which the English language is difficult for us to fully understand, and that's really comes down to a little bit of that, and how we look at that. And so we have this single or fixed composition and distinct properties. We can see these three copper kettles up here. They are mainly copper. There's probably some other stuff making it more of an alloy, but they are mainly copper. And copper is a pure substance. It's just copper, if they did it right. So what are types of pure substances? Elements and compounds. Now, sometimes we might think of a mineral as a mixture, but in a lot of times it's actually a compound, and I believe I took a class that required me to start to identify minerals at a much different way than your 8th grade science in college, and that we even had to memorize the chemical composition of of those minerals. And so they actually have a chemical formula that we have to worry about, and those elements are looked at as well. And the elements, so you can look gold and copper and silver, They are elements. It can't be broken down into simpler chemical means, and that's the smallest unit of a element is an atom. Now, when we get into the actual elements and identifying some of them, I'm asking that you are able to memorize about 56 of the 100, I think, 17 now on the periodic table. There might be. I might be wrong. It changes every year. But of those, we kind of say, we use this as about there's 112 elements on the periodic table. 81 of these occur naturally, and they're stable, meaning they're not radioactive. And there are about 20 that occur naturally that are unstable, such as uranium, plutonium. They are naturally occurring. You can mine them if you wanted to, not locally, but they're there. Some of the other elements are man-made, and that's how we come up with them. How they make them, well, there's methods that we can go into further, but just know that the newer ones are actually just man-made, so they're laboratory, CERN, hydrogen colliders, and things like that. That how they go through that. Now, the of the 100 plus elements, only about 10 of them occur, actually almost cover about 99% of the mass of the Earth's crust. Water and atmosphere. Oxygen, well, I'm pretty big fan of it. Don't know about you, but I'm a big fan of oxygen. What bothers some people is they see this silicon here and they're like, what? How? I breathe silicon? I'm not supposed to. No, you don't breathe silicon. And what they're looking at is, remember, Earth's crust. That the silicon is a major part of the Earth's crust. And so, and the same thing with aluminum, iron, and calcium. Those are major components of the Earth's crust. Now, oxygen is bonded a lot of times to silicon, aluminum, iron, calcium, and the remainder of the things. And so that's why it's such a major component. Hydrogen is also bonded sometimes to them, but it has such little mass that it's very, very small amount of it actually. Now, the chemical formulas, like we saw on a previous one when we were trying to figure out, when we had C2H6 on a previous slide, we saw that was a chemical formula. That was a chemical formula for ethane. Now, that's the name of it. The chemical formula is just a way to describe what's going on. The compound or most table salt, sodium chloride, the Na for sodium, and the chloride is from the Cl part of that. And we'll look at how those combine and do all those types of things as we continue on. But it's two or more atoms, and now you can get into like sugar and some of those things where you're going to start to get really massively large things. And so how these compounds look, they can be very small and simple, or they can be extremely complex. And that's why, because it can be so complex, is why sometimes we have to be very careful on the terminology that we choose. Some compounds, such as DNA, it is a compound technically, but because it is so large, a different term that we use is a molecule. And so because of how it behaves and how it acts, we look at that. The hydrogen molecule, which is seen as H2, because it's actually two hydrogens bonded together to form the H2, that is a smallest molecule we can have, and it's a molecule because it behaves as one entity, as if it were one as one thing. It is almost as if it were its own element. There are others as well. But you also have DNA, which has thousands of atoms. And it behaves as a single entity. Now we have to be careful about that. It's a compound, but because of how it behaves, it's better to call or use the term molecule. So we're going to use that. It might be confusing for some, but so if necessary, ask for, say, some clarification on that. Now, some people enjoy flowcharts, and you can write these down if you want. If not, you don't need to. But you kind of have a yes, is the matter mixture or is it a substance? And so you kind of go and follow the chart. And does it have a variable composition? Nope. Well, then it's a could be a substance. It could be homogeneous, or it could be a homogeneous mixture. And so you have to be very careful. Now, a lot of people think steel is just iron, but it actually has carbon and some other things, and nickel and some of the other things in there. And actually, if it's stainless, and depending on if it, there's usually some chrome in there as well. So we have to be careful. Granite, granite countertop, you can see all the little pieces. Nice compounds. You can see it's a mineral there. You got a ruby or of some sort, some bling bling action, I guess. And you have silver, which is just an element. And so you have all these different paths to follow on what is it? How do I identify which one is which? So that's the end of this chapter's notes. Please continue on and continue to progress forward.